This video is real quick about polar versus nonpolar molecules. So when we're talking about polar and nonpolar, we're talking about covalent bonds. That means all nonmetals coming together to share electrons. So their orbitals are overlapping to share electrons. Now you can either share electrons equally, that would be nonpolar, or you can share electrons unequally, and that would be polar. So nonpolar sharing equally, polar sharing unequally. And we'll know if things share it equally or unequally based on how much they love electrons. Here's our electronegativity table. Fluorine is the most electronegative. Anything up and close by him is being very electronegative. But you do have to remember the order of F, then O, then N. N is third electronegative, and O, you can see N is kind of equal to chlorine here. And then from there, it's just whoever is closest to fluorine. So, going a little closer into these things. We're going to decide if a molecule is polar or nonpolar. So the first thing we have to do is decide if the bonds are polar or not. I can look at oxygen, and I know he's very electronegative, and carbon is not very electronegative. So I would create polarity arrows that look like this. What that means is this side over here, the oxygen, is kind of negative because he loves electrons, and this side of the bond over here is kind of positive because he doesn't love electrons as much, hence the positive part here, and it points to the negative part. Same thing's happening on the other side. So these arrows would show polar bonds, but you technically would call it a dipole moment. That's like the vocab term that you would use in the AP world, is that it's a dipole moment. So I have two different dipole moments, and then I have to think about the molecule as a total whole. Well, if I kind of like think of the molecule as a whole big circle, it really is a circle when you think of it. Like all these molecules we make are just kind of like circle blobs. This circle blob happens to have a kind of negative side over here. It's a partial negative. And a partial negative side over here. It has two poles that are both negative. So really it doesn't have two poles. I wouldn't call this molecule a dipole because it has only negativeness on both ends. So although this has dipole moments or polar bonds, it's a nonpolar molecule. Going to a different one over here. If I look at H2O, O is very electronegative, so we'd see the arrows would go this way. But we can't think of it in a 2D structure the way I've drawn it. I have to think of it in the Vesper structure form. So Vesper structure would say this is a bent molecule. You must think of things in a structure that it's actually in 3D. So now if I look at my polarity arrows, I can see they don't cancel. The way I drew it up here, the arrows would cancel each other and you'd say, oh, that's nonpolar. But technically speaking, they have this bent structure. So your overall dipole moment is like this. In other words, this side of it is kind of negative and this side of it's kind of positive, which is why water is a polar molecule. Bringing it to the last one, it's a little bit tricky. If you look at P and H, actually if we go back to the electronegativity table here, you can see that P is worth a 2.1 and H is worth a 2.1. Now you wouldn't really know that because you can't possibly memorize all these numbers. And they're only looking at 2 sig figs anyway, so I think if you go to 3 sig figs, they are technically different. But let's say that they're the same. So electronegativity of H is 2.1 and of P is 2.1. So technically you would say that this doesn't have any dipole moment, or it doesn't have any polar bonds to it. But I would still say this is a polar molecule. It has an overall dipole moment because of these lone pairs up here. The lone pairs are like hanging out up there and they're super negative. So if I jelly bean this up, what I basically mean is make a big circle around it. This part of the circle at the top would be kind of negative, and this part of the circle at the bottom would be kind of positive. Once you create a positive and a negative side, two poles, you now have a dipole moment. This has an overall dipole moment, so it's a polar molecule. So anytime you have lone pairs in the center part of the atom, you really got to think about those lone pairs, because nothing can cancel out the negativeness of that. Even if I wanted to take and put an F down here and force like a dipole moment going that way, fluorine can't possibly complete with electrons. Fluorine has a nucleus and some positiveness in them, but electrons are just electrons. So nothing you put on the other side of these electrons are going to cancel them out unless you put another electron on the other side, which only happens for square planar. So I hope that helps.